Right, we have our last lecture here. It's about simple harmonic motion, which is just when an object is oscillating back and forth at a uniform rate, going up and down, something like that. And there's a lot of different formulas that come with it. And the first thing we look at is W, which is angular frequency, which measures angular displacement over time. So like how much it angularly displaces per second. And that is equal to 2 pi over t, which is the period, which is the amount of time it takes to complete one full rotation of the motion. And t is also equal to 1 over the frequency, which is just the inverse of the time it takes to do one rotation, which is the same, which is basically just how much rotations per second it does. So equals 2 pi f. And then through another formula, we can get that this is also equal to G over L if we're doing like a pendulum type swing. And if we're doing a spring type swing, which is the case in problems 33 to 35, it's equal to root K over M, K being the spring constant, but we don't really need to use that. And then another big idea is that to get the kinematic equations, to get, say, like displacement, it's basically just a sine function or a cosine function, a trigonometric function. And the amplitude, which is independent of all these other things, which is one of the key things that makes it simple harmonic motion, the distance to like the maximum displacement, is defined as the amplitude cosine of Wt, which makes sense to have this inside the parentheses to make it account for how quickly it goes back and forth. And again, we can take the derivatives of each to find velocity and acceleration, which is what we'll have to do to get number question 35. But this is the main idea of simple harmonic motion, is that it moves back and forth, and there's all these useful formulas that mainly have to do with angular frequency, W. All right. Question 33. We have a spring attached to basically the ceiling, and then it's attached to an object, and we are told that the object is pulled down 15 centimeters, and then since it's going to be swinging back and forth, it's also in simple harmonic motion, and the period it tells us is 2 seconds. And the question asks, what is the position of the object after 3 seconds? And all we really need to know for this question is what a period means. And in this case, or in all cases, a period is just how the amount of time it takes for the object to complete one full rotation, to go right back to its original position. And in this case, we start out at negative 15 centimeters all the way stretched out, and then it's going to go up at 1 second all the way compressed, and then going to go all the way back down to its original position at 2 seconds. Meaning, if we add 1 more second to 2 seconds, at 3 seconds, it's just going to go all the way back up to all the way compressed. That's going to be another second, another half period. It's going to go all the way back up to where it's compressed. And since the amplitude is the same either way you go, it's going to be positive 15 centimeters is going to be the position after 3 seconds, which is answer E.